Humanity has always been drawn to the idea of extending life, a fascination that dates back to ancient myths of fountains of youth and elixirs of immortality. While the allure of eternal life remains speculative, scientists are making strides toward increasing not just lifespan, but also healthspan, the period of life spent in good health. Today, laboratories around the world are actively investigating the cellular mechanics of aging, hoping to push back the limits of human lifespan and unlock the secrets of prolonged vitality. As modern science delves into the mechanisms of aging, researchers encounter a fundamental barrier known as the Hayflick limit. This limit, named after the scientist who discovered it, sets a cap on the number of times a human cell can divide. Each time a cell divides, the protective caps at the end of chromosomes, called telomeres, shorten. Once these telomeres reach a critical length, the cell enters a phase called senescence, where it can no longer replicate. This cellular aging process, akin to a ticking clock, serves as a natural constraint on the longevity of complex organisms. However, in labs around the world, scientists are studying ways to slow or even reverse aspects of cellular aging by focusing on telomeres, cellular repair, and other biological systems that contribute to the degradation of cells over time. Their findings suggest that while immortality may be unattainable, extending the healthy years of life, potentially by decades, could one day be a reality. But as we edge closer to this possibility, broader questions arise, challenging our understanding of what it would mean to live far beyond the current human lifespan. The Hayflick limit governs the aging process at the cellular level, representing the number of times a normal human cell can divide before it ceases to replicate. The underlying mechanism involves telomeres, structures found at the ends of chromosomes that prevent genetic material from unraveling during cell division. Every time a cell divides, telomeres become slightly shorter. Over time, these caps wear down, eventually signaling the cell to stop dividing and enter senescence. In this state, cells remain alive but lose functionality, becoming more prone to inflammation and contributing to the decline of organ systems. This process has led researchers to describe telomeres as biological odometers, marking the passage of time at a cellular level. Research has shown that telomere length can be influenced by lifestyle factors such as diet, exercise, and stress management. In some cases, telomeres have even been observed to lengthen under specific conditions, sparking hope for interventions that could slow or partially reverse telomere shortening. However, many challenges remain, as artificially extending telomeres could also increase the risk of cancer by allowing cells to proliferate unchecked. This double-edged sword poses a significant hurdle, as finding a safe method to maintain telomere length without increasing cancer risk is a delicate balance that has yet to be fully understood. Despite these challenges, scientists are making notable advances. Recent studies have demonstrated that telomerase, an enzyme that can add length to telomeres, has the potential to extend the replicative capacity of cells. Some research involving genetically modified mice has shown that activating telomerase can reverse signs of aging and improve health markers, sparking interest in human applications. However, translating these findings to humans is complex, as the risks associated with telomerase activation remain significant. Still, the research points to a tantalizing possibility. Slowing down the cellular clock could mean that human cells, and by extension, humans themselves, could live longer, healthier lives. While telomere length is a crucial factor in cellular aging, it is only one piece of a larger puzzle. Scientists are exploring additional pathways that influence the aging process, including cellular repair mechanisms, mitochondrial function, and autophagy. Autophagy, often described as the body's cellular recycling process, allows cells to break down and remove damaged components. By promoting autophagy, cells can maintain functionality for longer periods, reducing the accumulation of damage that leads to aging. Caloric restriction and intermittent fasting have been shown to promote autophagy, which may explain why these dietary approaches are associated with increased lifespan in animal studies. This process is thought to reduce the burden of cellular garbage, preventing the buildup of damaged proteins and organelles that contribute to aging. Likewise, mitochondrial function plays a significant role in cellular health, as these tiny powerhouses are responsible for generating the energy that cells need to function. As we age, mitochondrial efficiency declines, leading to reduced cellular energy and increased oxidative stress. Researchers are investigating ways to bolster mitochondrial function, which could help slow the aging process by improving energy production and reducing cellular damage. Advances in gene editing technologies, such as CRISPR, have also opened up new possibilities for combating aging at the genetic level. By modifying genes associated with longevity and disease resistance, scientists hope to create therapies that could extend the healthy years of life. While the ethical implications of gene editing remain a topic of debate, the potential to prevent age-related diseases and enhance resilience to cellular damage is a promising avenue for future research. Beyond laboratory interventions, lifestyle factors play a crucial role in the aging process. Studies have shown that lifestyle choices such as diet, physical activity, sleep, and stress management can significantly impact cellular aging. Diets rich in antioxidants, for example, help to combat oxidative stress, which damages cells over time. Physical exercise has been shown to improve mitochondrial function and promote telomere stability, while adequate sleep allows for the restoration of cellular systems, reducing the impact of aging. Stress is another critical factor, as chronic stress has been linked to accelerated telomere shortening. Techniques for managing stress, such as mindfulness meditation, have shown promising results in slowing down telomere attrition, suggesting that mental well-being is closely tied to cellular health. While these lifestyle factors may not prevent aging, they can help mitigate its effects, highlighting the importance of a holistic approach to longevity. The potential to extend human lifespan raises significant social and ethical questions. If future breakthroughs allow people to live for many additional decades, how would this impact society? One of the primary concerns is access to life-extending therapies. If these treatments become available, will they be accessible to all, or will they remain within reach of only the wealthy? This disparity could exacerbate existing social inequalities, creating a world where the affluent have the means to live longer, healthier lives while others face shorter lifespans and increased health challenges. There are also questions about the environmental impact of extended lifespans. With a growing population and finite resources, longer life expectancies could place additional strain on ecosystems and infrastructure. Increased lifespans would necessitate changes in retirement systems, healthcare, and resource allocation, forcing society to adapt to a demographic landscape where people live far beyond the current average lifespan. Moreover, the psychological implications of extended lifespans are profound. If people could live for 150 years or longer, how would this alter the way individuals approach life? Goals, relationships, and careers might be redefined, as people could have multiple careers or families over their extended lifespans. The societal rhythm of life stages, education, work, retirement would also change, creating a need for new social structures and support systems. There are also concerns about whether extended lifespans could lead to societal stagnation. In a world where the older generations live much longer, would younger generations have fewer opportunities to lead and innovate? This question touches on the balance between preserving wisdom and creating space for new perspectives, an issue that could have profound implications for cultural and technological progress. The quest for longevity is no longer confined to the realm of science fiction. It is a reality being pursued by scientists and researchers around the world. However, achieving breakthroughs in life extension will require more than just scientific advancements. Society must also prepare for the ethical, social, and environmental challenges that accompany extended lifespans. Public discourse around these issues is essential, as decisions about who receives access to life-extending treatments and how resources are allocated will shape the future of humanity. Policymakers, ethicists, scientists, and the public will need to engage in discussions about the value of extended life and the responsibilities that come with it. As research progresses, the concept of aging will likely evolve. Aging may no longer be seen as an inevitable decline, but as a modifiable process, open to intervention and improvement. However, it remains to be seen whether humanity will embrace this potential shift or adhere to traditional perceptions of the human lifespan. The journey toward extended lifespans will require careful consideration of the costs and benefits, both on an individual and societal level. The scientific pursuit of longevity holds promise for enhancing human health and extending the years of life spent in good health. Yet the journey is fraught with challenges, both scientific and ethical. The dream of living far beyond our current lifespan raises profound questions about the nature of life, death, and what it means to be human. As researchers continue to unravel the mysteries of cellular aging and develop interventions to slow the aging process, society must grapple with the implications of a world where lifespans stretch far beyond current expectations. The road to longevity is still in its early stages, with more questions than answers. However, the pursuit of extended life, fueled by advances in telomere science, genetic editing, and cellular health, offers a glimpse of a future where aging may be managed, if not entirely defeated. Whether this vision will ultimately lead to greater wisdom, equity, and resilience, or create new social and ethical dilemmas remains to be seen. In the meantime, the quest for longer, healthier lives continues, bridging the gap between science and the timeless human aspiration for life beyond boundaries. As we explore the science and future of longevity, it's clear that the journey to extended, healthy lifespans is both exciting and complex. While we're making strides in understanding the cellular processes that govern aging, there are still many challenges and ethical questions to tackle. But who knows? In a few decades, living to 100 or even 150 in good health might just be a reality. Thank you for joining us on this journey through the science of aging and the possibilities of human longevity. If you enjoyed this video, don't forget to like, subscribe, and hit the notification bell so you never miss an update. We'll continue to dive into the latest in science, health, and technology to bring you the insights shaping our future.